Okay, so yeah, this is the fourth quilt day, and this is my first quilt day talk. So thank you for your patience in listening to me. A common theme with some of the talks that have been presented have to do with distinguishability, this concept of how distinguishable are quantum states. That's useful from a practical perspective. We're trying to communicate information from one, New Orleans to Baton Rouge, for example, to give us news about hurricanes that are coming, for example. So the idea of this work is to formalize this notion into what's called the resource theory. To think of distinguishability as actually a resource. If there's more distinguishability, you can make decisions faster, right? And so it's useful if states are more distinguishable from one another. So that's the basic idea. This is joint work with Xin Wang, who's become a very good collaborator. He's visited LSU a few times. He was a postdoc at University of Maryland, and very recently he has moved to China to work for Baidu in their research wing in quantum information and quantum computing. You might read in the news that there's a big buildup in quantum information expertise in China, and so he'll be part of that effort. This is based on two papers that we put in the archive recently, one of which was about a week ago. So I should also indicate that in some sense this is a practice talk, because I'll be going to a conference next week in Banff, in Canada, to deliver this talk at a workshop. The title of the workshop is Quantum Resource Theories. Okay, so it's very relevant for that. So if you have constructive criticism that's TV friendly, please let me know. Okay. Good. So let's move along. As I was saying, distinguishability is kind of the central concept. We're seeing this theme come across in many of the talks today. If you're doing experiments, often you do repeated trials to get more data, such that you can make an effective decision, for example, about what state your experimental device was prepared in. In this talk, we're going to be focusing on the scenario where there's just two different hypotheses. That's actually the simplest possible scenario you could think about. And there are different variations. One will be about distinguishing quantum states. An extension of the theory is about distinguishing quantum evolutions, which we also call quantum channels. Okay, I don't know if we'll have time for that. I don't want this to be a tortuous talk, and we want to go eat at some point. So it could be that all I could talk about would be quantum states, and that would be it. And that's fine. And if you have questions as this is going along, I encourage you to speak up. That's part of the spirit of Quilt Day, I would say. Okay, so if the two different hypotheses are somewhat distinguishable, then fewer trials will be needed to arrive at a decision. So as I was saying, this is how we can think of distinguishability as a resource, okay? And one of the goals is that we want to quantify this resource, okay? The spirit is similar to what people have been doing for over 2 decades in entanglement theory. One of the original insights of Charlie Bennett, John Smolin, and others was to think of entanglement as a resource that you can quantify. How many pure maximally entangled states can you distill from a given quantum state? And if you can get these maximally entangled states, those are useful for things like teleportation, or superdense coding, or quantum computing, or quantum key distribution. Entanglement has a lot of uses, and so people are very happy and pleased to work on that. And so I guess I'm trying to convince you that distinguishability is maybe just as interesting. Okay, so we want to quantify this resource. We have to get a strict mathematical framework, okay? And the mathematical framework will be related to what's called quantum hypothesis testing. If you took a course on statistics, you learned about type 1 and type 2 errors, And so, you know, we have extensions of those notions in quantum labs. Okay? So the main message is that we're going to develop this resource theory of asymmetric distinguishability, and the outcome is that many, I would say, beautiful results emerge that are somehow quite pleasing if you've studied distinguishability and hypothesis testing before. It's funny, this idea was proposed in, this work could have been done a decade ago, you know. So this was proposed by a quantum information theorist from Japan. His name's Keiji Matsumoto. And I think this paper essentially went unnoticed by the larger community. If you look on Google Scholar, it has only 3 citations, which is some kind of signal. And you know, so we're in some sense developing this proposal from a decade ago in much more detail. Okay? The reality is that we developed it first, and then I went out to look in the literature and saw that this work was out there. I was like, oh, okay, so we must cite. Okay, so one of the ideas when you're establishing a resource theory is to identify what is the basic unit of the resource, right? In entanglement theory, the basic unit is what we call, there's many different names, EPR, pair, Bell state, E-bit for entangled bit, okay? And that's the basic unit resource of entanglement theory. And so one of the original contributions of this work is to identify what is the basic unit. And it's something we call the bit of asymmetric distinguishability, which is a bit of a mouthful, so I might just call it an AD bit. Okay? And then also the objects to manipulate are things that we call a state box, which is like a black box that contains a quantum state prepared in you know, it's a quantum system prepared in one of 2 states, and you don't know what that state is. Okay? I'm going to say more about that on the next slide. And then this notion of the black box or the state can be extended to a quantum channel black box, and then even something, a further generalization of a quantum channel called a quantum strategy. And then there are these basic tasks to consider, which are distillation of these bits, okay? That's like you're trying to extract distinguishability from the box that contains the states, okay?
Can you explain again what is asymmetric distinguishability?
We're going to get to that.
Oh.
You're going to see it very precisely.
Okay.
Yeah. Okay. Good. And then there's another task called dilution. So in entanglement theory, what is dilution? That's where if you're given a bipartite state, rho AB, a density matrix, rho AB, you want to figure out what is the cost to produce that state from local operations in classical communication. So you want to know, starting from a maximally entangled state, which is like the pure form of entanglement, how much of those does it cost to prepare a given quantum state? That's another way to quantify entanglement. So we're going to consider that here as well. And so that's the concept that's unusual from the perspective of the statistics literature. If you look in the statistics literature, I don't know if this concept is there at the forefront, okay? But it's a fundamental way of thinking from kind of a thermodynamical or physical perspective. You know, if you have one forward process, it's somehow natural if you're doing physics to think about the reverse process, right? That's something we think about a lot, like Carnot cycles, et cetera. Okay, and then more generally, we want to know how we can convert one state box to another state box. What is the cost of doing that? First of all, can we do it? If we can't do it, can we do it with some error? Okay, and that's going to connect with the asymmetric distinguishability. And then we're also going to phrase an asymptotic version of this question. Okay, so that's kind of the framework. And what we'll find is that these tasks of distillation, dilution, will give a physical or operational meaning to entropies that have been out there in the literature for many years now, and are used in analysis of other tasks. You know, like if you're talking about quantum key distribution, and you want to know how secure is the key that you've made, you end up using this quantity called max relative entropy. Okay, and then there's the smooth version of it as well. And so these quantities that have existed for at least a decade in the literature, we now give them a core meaning in this resource theory. Okay? And then there's an information measure that is kind of pervasive throughout quantum information theory, which is called quantum relative entropy. It's a relative notion of the von Neumann entropy. And this is the quantity that emerges as the fundamental exchange rate. Okay? So if you think of the US dollar, for example, as the fundamental exchange rate. I don't know, I'm an American, so maybe I do that. This is like the US dollar, okay? Good. So now I'm going to get into some more details and tell you a bit more more precisely, what is a state box? Okay, so I literally think of it as just physically, it's a quantum device or a qubit or whatever that I can prepare in one of two states, rho or sigma, which is the density operator that describes the state. And then I do this and I hand it to you, and I don't tell you which state I prepared, right? And so then you're then the agent in the resource theory, and you're allowed to manipulate the state box in whatever way you please, right? And so one manipulation you might want to do is to figure out which state was prepared, right? You might want to figure out whether rho or sigma was prepared. That's related to state discrimination. Another thing you might want to do is try to convert it to another state box, okay? And so that's something we'll talk about as well. So yeah, what can you do with the state box? In this resource theory, we allow any possible quantum channel. Okay, so what does that mean? I think of that as any possible quantum physical evolution that you can do in this state. So, that could be a unitary rotation. It could be a measurement. It could even be throwing the state box away. That's something you could do if you don't want to play the game in the resource theory. Okay. So basically, you can do anything. Mathematically, this is what's called completely positive trace-preserving math. That's the lingo, if you want to know the precise mathematical description of what is a quantum channel. But I'm not going to get into details of what that is. Okay, so one basic manipulation you can do is you can say, well, I have this state box, and then mathematically we're going to describe it as this ordered pair, where the first slot is rho and the second slot is sigma, and then you're allowed to do a quantum channel. And so in this box, you have either rho or sigma, and if you do a quantum channel, it will evolve to n of rho, which is the evolved state, or it evolves to n of sigma. Okay, so you got a new state box with a different pair of states that's related to the original pair. So that's a basic manipulation. Some channels that you do, you can undo, right? And what are those? Well, unitary evolution, right? That's a basic principle of quantum mechanics, that we have unitarity, and thus in principle we can undo things. And so if we take rho and sigma and do a unitary quantum channel, then we can go back. Okay? So in some sense, in that sense, these boxes or pairs of states are equivalent in the resource theory, because I can go from one to the other and go back. And so you can do that as many times as you want, and there's no loss in distinguishability if you do that. Okay? More generally, we have what are called isometric channels, which can also be done. That's a generalization of a unitary. Okay? Another thing you can do, if you so please, is you can take your state and tensor in, bring in some quantum system in another state, right? And maybe that could help you in some way to perform a measurement that would try to identify the state. Often when you do measurements, we talk about projective measurements, and that's somehow a measurement on the system itself. But in any experimental implementation of a measurement, what you do is you bring in another quantum system in some standard state, and then you do some kind of coupling, and then you measure the ancilla state, ancilla system, to figure out something about the original system. Okay, so you're allowed to do this as well, but this is something that doesn't change distinguishability at all, right? So you could bring in this system in a given fixed state that we'll call tau, and then how do you get back? Well, you can just discard what you brought in. That's called partial trace. You just throw it away, right? So those are things that you can do for free, and they're reversible. Okay, and so a fundamental question of the resource theory is this question. So the input data for the question is, you're given two state boxes. The first state box contains rho and sigma. The second state box contains tau and omega. And then you want to know, can I get from the first one to the second one? Right? Is there a quantum channel that'll take this state box to this state box? Okay? So that's a basic question of the resource theory. It's perhaps, well, there's going to be a more general one that we'll get to. And you can think of it as, it's the same as this question. So we want to know, given rho, sigma, tau, and omega, you're given the description of those density matrices, is there a quantum channel such that these equations are satisfied? Okay? So the constraint on the quantum channel is that, well, it has to be a physical evolution, right? If you're allowed any linear map, you could do this as you please, but we have the constraint that we want this to be a physical quantum channel. Okay. You may not realize that this question has a tremendous history. So this is the value of looking in the literature. And it goes all the way back to a statistician named David Blackwell, who did work in 1953. He's actually quite a remarkable individual. He's the first African American to be inducted into the U.S. National Academy of Sciences, the seventh African American to get a PhD. So that's pretty remarkable. And he faced a lot of obstacles, but had tremendous insights into hypothesis testing and statistics. Okay, and then came some work in I'm probably missing a lot, okay, so, but I mean, that's like 30 years, and please forgive me. But then came some work from Alberti and Ullman in 1980, and they looked at particular instances of this. And then, okay, I'm probably missing a lot of stuff again, and then people that I know got interested in the problem. So I'm citing their work very carefully, okay. Okay, so it has a long history and many insights have been made. One of which is, I guess came later, and this is something that Chris was hinting at in his talk, is that you can solve this problem algorithmically by a technique called semi-definite programming. Okay, so this idea of semi-definite programming plays a fundamental role in all of quantum information theory because the objects that we're dealing with have semi-definite constraints. Like a density operator is a positive semi-definite matrix, right? It has trace equal to 1. That's a semi-definite constraint. It's a linear constraint, okay? So somebody has to keep me on time because I can't be my own chairman, so just be careful and don't let me keep talking. It goes by a different name. Quantum relative majorization is a term that I saw in this paper of Francesco Buscemi and Gilad Bohr, who will be the organizers of the workshop in Canada next week. And this connects to something called majorization, which is a notion in mathematics, which has played a role in quantum information as well. Okay, so in principle, this can be solved by semi-definite programming. What does that mean? If you're given the mathematical description of rho, sigma, tau, and omega, you can plug that into your computer in MATLAB, and then you can press a button, and you would know the answer in time, polynomial, and the dimension of the states. Okay, so you would know it quickly. If you're dealing with small dimensional states. If we're talking about n qubits, then the dimension is exponential in n, and so it's going to take a long time, right, in that case. So it just depends on what you're looking at, and then, if you want to be dealing with 1,000,000 qubits, then this is not satisfying for you, right? So because it's going to be a large space to optimize over. Okay, so where do we come in? At least where do we think I come in originally? Maybe I'll be corrected next week in Canada. We had the observation that, you know, in practice, if you want to do an exact transformation, you can't really do that in the lab, right? You can't do an exact transformation, right? And when you're doing things in the lab, and you solve this on your computer with a semi-definite program, you find the channel that does the transformation, and you say, hey, now I want to do it in the lab, right? You're not going to be able to satisfy these equations exactly, right? You're always going to commit some error in the lab. Okay, so we made that observation, which I guess is maybe a simple observation to make. The other observation regarding the modification that we make is that if the transformation is performed with a small error, then you're really not going to notice it in practice, and so maybe that's okay. And then we want to revise the problem to understand, well, can we do the transformation with a little bit of error? Okay. And so the way that we modify the question is this way. Given the state boxes, how well can a quantum channel take the state box, the initial state box to the second one approximately? Okay? And then the notion of approximation is this, okay? And so this comes back to Lior's question about why asymmetric. And so the way that we're going to modify things is, and you may criticize me here, but we'll demand that this sigma goes to omega exactly. Okay, that's what we'll demand mathematically, and there's good reasons for doing that, which I'm happy to convince you of. And we'll allow for an epsilon error in the conversion of rho to tau. So the errors are asymmetric, and that's why it's asymmetric distinguishability. Okay, so that's where the name comes from. Okay, so that's like a very fundamental question of the resource theory. And I want to tell you more about the notion of error. Okay, in some sense, this is the exclusive notion of error that maybe everyone should be using to quantify error. And there are good reasons for doing so. And there's a very forceful blog post of Earl Campbell, who's in the UK, who convinced me, really, there is no other. I mean, I should have been convinced before that, but this really said it for me. And we spent a few days debating what should be the notion of error, but we ultimately arrived on this after being forced, by this blog post of Earl. And so what is that notion? This is a shorthand that I'm showing here. If we have states zeta 1 and zeta 2, when I write approximate epsilon, this is what I mean. That the trace distance, the normalized trace distance between zeta 1 and zeta 2 be no larger than epsilon. Okay? And I should tell you what trace distance is mathematically, just so you have a sense of how you calculate this. You take an operator A, you do A dagger A, you take the square root of that, which just means taking the square root of the eigenvalues, and then you take the trace. Okay, so that's trace norm from which the trace distance is induced. Okay, and why is this the measure that we should use? Well, there's an old theorem of Carl Hellstrom from 1969, which says that in any experiment you could do, when you're trying to distinguish zeta 1 from zeta 2, if you compute the deviation in probabilities that you would observe from the experimental outcomes, and then you optimize over all possible measurements you could do to distinguish the states, this is what you get. Okay? So it's a measure of deviation between observable probabilities. And that's what the blog post hammers home. Okay, so that's the notion of approximation we use. Fortunately, this itself can be calculated by a semi-definite program. Okay? The trace distance itself can be calculated by a semi-definite program. So it can be brought into other semi-definite programs as like a part of it where you're having an optimization. Namely, this is the formal mathematical statement of the problem that I wrote in the previous slide, which we call the approximate box transformation problem, okay? So what are we doing? We're trying to figure out the smallest error that we could have when transforming rho to tau and sigma, and we want sigma to go to omega exactly, okay? We want to make this error as small as possible, and we're optimizing over all quantum physical evolutions, okay? So that's the basic that's a basic problem of the resource theory. And if you work a bit, and if you use the fact that in fact optimizing over quantum channels is that there are semi-definite constraints that specify what a quantum channel is, then you arrive at this. Okay, so that might just look like a big blob of symbols, but yeah, it does. So, but this is something that you could plug into your computer, and then you would know the answer. You would know the smallest epsilon with which this transformation can be conducted. I'll explain a bit what this means. This constraint has to do with trace distance. This corresponds to the epsilon that you're trying to minimize. Okay. This is the constraint that sigma has to go to omega exactly. It's rewritten. And then this is one of the constraints for n to be a quantum channel. Okay. And then the other constraint is that this J operator should be positive semi-definite. Okay. So we've taken all the constraints in the problem and incorporated it in this compact notation, which you could then go program your computer to do. And then if you run your program and you find that the answer is 0, you can do the transformation exactly. All right, any questions on this? This might be a natural question time. I don't know.
If you take the infimum,
Yeah.
still you can get some operation to do that, or
Yeah. From the program, you can also learn what the optimal channel is, or at least what n optimal channel is.
because you're taking the infimum, I'm not sure you can get it.
We're trying to make the error as small as possible.
I think he's asking whether infimum can be achieved.
Oh, I'm sorry.
Yeah.
This is a minimum. I tend to just write infimum because that's what I do. But just anytime you see infimum, replace it with minimum.
Okay.
Yeah. Okay, so it raises a good point. What if these are infinite dimensional states, right? What if these are bosonic states, like coherent states? Can we still do this? In principle, this is the program you would run, but since the dimension's infinite, maybe it won't stop running. Okay. But you could incorporate maybe some kind of energy constraint cutoff to make the effective dimension finite, and then your program would stop at some point. Okay. But that's part of the reason I put infimum there, because this still will, in principle, apply to infinite dimensional systems. Okay. Good. And 15 minutes. And 40 slides. Okay, so another version of the problem is the asymptotic version of this problem. And so the idea now is, let's change things a bit. We said that this is somehow unsatisfactory. What if we have n qubits and n is very large? Then we're not going to get an answer, right? So what I want to do is change the problem where if we're talking about many qubits, then we can get interesting answers that tell us about distinguishability and state transformations. Okay, so what we'll do now is change our thinking to think like the pioneer of information theory, Claude Shannon, and Charlie Bennett, the pioneer of quantum information theory, who was really one of the first to think about entanglement theory and these kinds of transformations of entangled states that people in the classical world did not think about. Okay, And I'm very excited. I don't know if you know what the Shannon Award is, but this is, you could call it like the Nobel Prize of Information Theory. We're all very excited that Charlie Bennett won this year the Shannon Award. He's the second person to win it of all time. And the first was Halevo back in 2016. So Bennett won it this year, and he'll deliver his Shannon lecture in Los Angeles in summer next year. The story I heard is that he didn't know he was going to win. He was at the reception of the conference. Andreas Winzer, who's a colleague of mine, was there with him. You know, maybe Charlie's getting a bit older now, and it was late, and he was kind of ready to go to sleep, you know, to go back home, and they hadn't yet announced the Shannon Award winner. And Andreas said, "You might want to stick around for a little more." And then, thankfully, you know, he won, and then went up and gave some short speech or something. Okay. Anyway, so we're now going to think about the asymptotic version of this problem. And so, what does that mean? I'm gonna talk about an asymptotic box transformation problem. So I want to fix numbers, integers n and m, and an error epsilon. Okay, and I'll say that in nm epsilon box transformation protocol, what the inputs of the problem is these numbers and two state boxes, rho, sigma, tau, omega. And then so a protocol is such that there is some channel that converts n copies of rho to m copies of tau, approximately, and it converts n copies of sigma to m copies of omega. Okay? So now we're going to the many copy scenario, which is, you know, similar to what Chris was talking about in his talk. Okay? And what we do to make the problem asymptotic is we coarse grain away these parameters, epsilon, n, and m, and we focus on a single number, which is the rate at which we can accomplish this transformation. So it's like, how many of the second box can we make from the first box? Approximately, but we allow the error to get small as n gets large. Okay, so that's thinking in Shannon theoretic terms. Okay? And the optimal rate is this quantity that's operationally defined in this way, so it's well defined. And we set it equal to the largest achievable rate, the supremum or maximum achievable rate. Okay? That's how it's defined. And what is the main result? This is our solution of the problem. Okay? So this is where the quantum relative entropy comes into play as the fundamental exchange rate. Okay? So the largest achievable rate is equal to the ratio of relative entropies between, you know, the relative entropy of the first state box and the relative entropy of the second state box. That's one of the main results. Okay, so that's a non-obvious insight of this work. The quantum relative entropy was defined back in 1962. If you study classical information theory, you've probably seen classical relative entropy. And so this is the agreed upon quantum generalization of the classical notion. There could be many other ones, but this is the one that has emerged to find the physical meaning, and now a physical meaning in this sense. Okay. So what it's saying, you know, quantum relative entropy is itself a measure of distinguishability. So if rho and sigma are the same, this quantity is equal to 0. Okay, the quantum relative entropy itself. If they're distinguishable, it's larger than 0. Okay, but it tells you how distinguishable the states are. Okay, so this is I would say the fundamental information measure in quantum information theory, from which all the other information measures are derived. Yeah. Okay, so what this result does is it highlights the principal role of quantum relative entropy in this resource theory. Another thing that happens is that the resource theory is asymptotically reversible. What does that mean? I could go from the state box, rho sigma to tau omega at this rate. If I want to go back, what is the rate there? It's going to be the inverse of this rate, right? You multiply the rates, that's 1. Okay, so you can go back for free. There's no loss. If you go forward from rho sigma to tau omega, in the asymptotic case, you can go back. Okay, so that's a very nice aspect of this resource theory. And it allowed us to solve an open problem in channel distinguishability that has been open since I stated it with co-authors back in 2016. So I thought it was an open problem. I thought it was an interesting open problem. Others do agree as well. But anyway, it solves this problem that we've been thinking about for a long time. Okay? But there is still more to do there. Okay, so there's actually not too much time left, and that's fine. So I'm going to give you a sense of how we arrived at this result. Okay, so inspired by Shannon, and well here, more so Bennett, we'll break the task into 2 different tasks. One which is distillation, the other is dilution, okay? So in distillation, what you're trying to do is you're trying to extract these fundamental bits of asymmetric distinguishability, which I haven't talked about yet. You're trying to extract as many of those as you can from this state box. So you're trying to extract the pure form of distinguishability from this state box. Okay, and then in dilution, what is dilution? That's maybe if you, it's like the opposite of desalination. So if you're, trying to get pure drinking water from salt water, that's distillation. The reverse process is dilution. You might ask from a practical perspective, why would you do that with salt water? But in quantum information theory, it's something that makes sense. Okay, so what you do is you break the task into 2 different ones. You first do distillation to distill the pure form of distinguishability, and then you do dilution to take those and prepare the desired state box. Okay? So that's the main idea of the achievability part, and then there's 2 parts to this theorem. First is like, how do you do it? And the second part is it optimal? Is the scheme that you came up with optimal? So we proved the converse part, and we used some technical tools that I don't know how interesting you'll find them. The people next week will find this interesting, I think. But it's kind of a relation between what's called sandwich Rényi relative entropy and a metric called fidelity. And this was a new mathematical contribution that we made, and then you use this in something called data processing, and you get the optimality. Okay, so that's the main idea. So what I'll do in the remaining time is talk about the pure form of distinguishability. What is the bit of asymmetric distinguishability? It's this simple box. Okay? So if I would have asked you, what do you think is the bit of asymmetric distinguishability, your immediate response might be orthogonal states, right? It's completely reasonable. But it turns out in the resource theory of asymmetric distinguishability, that actually is the most extreme form. That corresponds to an infinite number of bits of asymmetric distinguishability. So it's kind of surprising. But it's related to this asymmetry and the fact that relative entropy emerges, and relative entropy of orthogonal states is infinite. Okay? But I can just say it at a plain level, it has to do with the asymmetric error that we imposed in the resource theory. Okay, so the basic unit is in fact this. It's the first state in the state box is 0, and the second is a random qubit, the maximally mixed state. So this is a mixture of 0 and 1, okay? And you know, if you have just a bit of asymmetric distinguishability, that's not very useful. Like in any resource theory or in anything really, if you have just a bit, you can't do much with that, right? If I give you a computer and I say, oh, I'm going to sell you this computer with 1 qubit, you would not buy it, right? Okay. That would be a completely useless computer. And so on its own, a single bit of asymmetric distinguishability is not very useful. But it becomes more useful if you have more bits of asymmetric distinguishability. So this is how we define m bits. So you take the states and you tensor them m times, right? That's related to what Chris was talking about in his talk, that if you take more copies of a state, they become more distinguishable. Right? So this is the basic, this is m bits. And you know, with this maximum mixed state of m qubits, it's a mixture of all m bit strings, one of which is 0, which will have probability 1 over 2 to the m, and then everything else will have probability 1 minus that. Okay? And so we could do a transformation that's allowed in the resource theory to take m bits of asymmetric distinguishability to this state, where this is now just a single qubit, but pi 2 to the m is this state here, with weight 1 over 2 to the m on the 0 state, and then the complement on the other. And so the point is that as m gets larger and larger, the first state becomes more distinguishable from the second. Okay? And then as m goes to infinity, what do you get? You get orthogonal states. That's what we talked about. That orthogonal states are the most extreme. Okay. So this is actually a natural stopping point, I think. And then I had all kinds of mathematical details of what distillation is and what dilution is. But I can just explain it in words. Distillation, you're trying to take a state box and extract as many bits of asymmetric distinguishability as possible. You're trying to extract this state box with m as large as possible. Okay, so that's the distillation task. So you're trying to extract as much as the pure form of distinguishability as possible. And in dilution, it's the opposite process. You're trying to use as few bits of asymmetric distinguishability as possible to prepare some state box. Okay? So the idea there is that this resource is useful, and so you want the cost of preparing a state box to be as small as possible. You want to consume as few of the precious bits of distinguishability as possible to prepare the state box. Okay. That's the basic idea. So, you know, and if you're interested, I can tell you about the other 36 slides. Okay, so let's stop here. Thank you.